Hi, everyone, and welcome to the second week of our topological data analysis and neuroscience class. So this week, we'll be going over the sort of fundamentals that we'll need for the rest of the class. So this includes things like topology, metric spaces, and continuous maps. Okay, so we're going to start out with a formal review of topology. So last week, we took a very informal approach to topology. Today, we're going to go very into the details. So a topological space it consists of a pair of sets. So the first set X, this is sort of our base set, while the second set tau consists of a collection. So tau here is a collection of subsets of X. So you can also think of tau as a subset of the power set of X. And tau has to satisfy certain rules. So the first rule is that both the empty set and the whole space are in tau. The next rule is that the union of arbitrarily many sets in tau also has to be an element of tau. And the final rule is that the intersection of only finitely many elements in tau is again an element of tau. So we'll look at why we want those conditions in a second. But first, open and closed sets. So we talk about the sets in tau as open sets, and then the sets whose complements are open are going to be the closed sets. Okay, so the first example is the discrete topology on a set X. So the discrete topology is just the entire power set, right? So normally a topology is a collection of subsets of X. Here, we're going to take the biggest possible collection. We're going to take every single subset. And of course, the discrete topology is going to be a topology because, well, of course, the empty set and the whole space are subsets of X. And then also the power set is closed under unions and intersections, right? A union of subsets of X is again a subset of X. An intersection of subsets of X is again a subset of X. So that's why the discrete topology is a topology. Now the indiscrete topology, right? So the discrete topology is the largest topology you can put on a set. The indiscrete topology is the smallest topology, right? Every topology has to include both the empty set and the whole space. The indiscrete topology, however, includes nothing else, just those two sets. It's not a very interesting topology, but it is a topology nonetheless. Now, to go into a much more interesting example, the Euclidean topology. So the Euclidean topology is one we'll actually see quite frequently. And right now, we're just going to look at the Euclidean topology on the reals. But you can also look at the Euclidean topology on higher dimensional space as well. So R to the D, if you want. And we will look at that later on. But for now, let's just focus on the real line. Okay, so on the real line, so here I'm drawing the real line. And the open sets on the real line are just going to be unions of open intervals. So open sets are going to look something like this. Maybe we have this interval, union this interval. And maybe we have these two unioned with this interval here going off to infinity. Now, each of these itself is an open set, but their union is also an open set. So this is one mistake a lot of people make when they're first learning topology, is they think that the open sets here are just these open intervals. They are actually unions of open intervals. So these three intervals together is a single open set. Individually, they're also all open sets, but together they also are an open set as well. And so, yeah, of course, this Euclidean topology here, it contains the whole space just because the interval from -infinity to infinity is an open interval and it's the whole of the real line. It contains the empty set just because the empty interval. And then then the other two properties we need are, it needs to be closed under unions. So that is, if we take a union of these open sets, it needs to again be an open set. Well, here our open sets are just unions of intervals. So if we take that, what that's saying is that if we take a union of unions of intervals, it needs to be, again, a union of intervals. That is, of course, true. And then it needs to be closed under finite intersections. Now, this one is a little more subtle, and we can see here why we need the finite condition. Let's look at what happens if we try to require infinite intersections be open. Infinite intersections of open sets be open. So I'm just going to redraw this line. Okay, so we have a real line here. Let's call this 0. What we can do is we can take a infinite collection of open intervals. We're sort of converging onto a single interval. Let's call it -1. What we're going to do is we're going to take an infinite collection of intervals that are getting closer and closer to this, but converging. So the distance is getting smaller and smaller apart. So these are getting closer and closer to the interval -1, 1, but they're never quite getting there. But if we take the intersection of all these intervals, what we'll wind up with is actually the closed interval from -1 to 1. That's not something we want, right? We don't want an intersection of closed sets. Sorry, an intersection of open sets to be closed. There are certain situations where you want that, but definitely not here. And yeah, but we don't have to worry about that because this is an infinite intersection, and we only need to require topological spaces be closed under finite intersections, which here, if we look at the finitely many intervals that I've actually drawn, it is the intersection of all these is an open interval. Right? The intersection of all these is just the smallest one I drew, this to there. So this is one of the main examples of a topological space. Okay, so now another big class of examples is going to come from metric spaces. So you can think of a metric space as just a set with a notion of distance between elements in the set. So really what this is we have a set X and a function defined on pairs of points of X. So you want to think of this function as assigning to any pair of points the distance between those 2 points. And we want this function to satisfy certain conditions. So the first condition here is that the distance between any 2 points is always greater than or equal to 0, right? We don't want to have anything with negative distance, any 2 points with negative distance between them. The next condition we want is that the distance between a point and itself should always be 0. Note that this is an if and only if. So if the distance between 2 points is 0, then those 2 points have to be the same as well. The next condition is symmetry, right? The distance between X and Y should be the same as the distance between Y and X, always. And the last condition here, this one right here, is the triangle inequality. And so it's helpful to draw it. So what this one says is that if I have 3 points, X, Y, and Z, well, the distance from X to Z should be at most the distance from X to Y plus the distance from Y to Z. So in this situation here, right, the length of this side of the triangle is much less than the length of this side plus the length of this side. That's fine. What this is just saying is that we just need it to be less always. Okay, so an example of a metric space, and this is going to be one of the main examples for us in this class, is Euclidean space. So this is just R to the D, right? So just a real, like, for example, R1 is just the real line, R2 is the real plane, R3 is three-dimensional space, and so on. With this metric here, so this is the 2 norm, right? The 2 distance, and we'll look at this right now. So let's look at R2, comma D2. Okay, so the space here is all of 2-dimensional space. And the way we can define a distance between 2 points is what you would do in, for example, high school geometry. And if we have 2 points, x1, x2, so let's call this point here x. We have another point y, which is say y1, y2. The distance between these 2 points is just the length of a line segment between the 2 points. So just the length, or we can write this down, Pythagorean theorem, as distance between x and y, square root of x1 minus y1 squared plus x2 minus y2 squared. And you can check that this distance here satisfies all the conditions on the previous page. We're not going to go through that. It's a bit tedious. But there are also other metrics we can define on this set here, R2. There's something called the Manhattan metric as well. So this here is the Euclidean metric. We can also define, there's a whole lot of metrics we can define. We can define the Manhattan metric. This is right, it's the same, it's a metric on the same set. We're going to give it a different name now, D1. And the way we define this is, you want to think about this like you're walking in the city. If you're walking in a city, you can't right, the shortest distance between 2 points is a straight line, but you can't always go in a straight line in the city. Right, you can't just go straight through buildings. So if you're walking in the city, you're oftentimes going to have to go around the corner. So that's why this is called the Manhattan metric. It's like you're walking on city blocks, right? You have to go over and then up. And so the Manhattan metric is basically the sum of these two side lengths here. It's you go this far and then you go this far. And so we can write this down as D2 right here. So here D1 of x comma y it's going to be the sum of the differences. So just the absolute value of x1 minus y1 plus the absolute value of x2 minus y2. There's a whole host of other different metrics we can put here. One I'd like to point out that's not very interesting, but these trivial examples are always good to keep in mind, is the discrete metric. So here, the metric is going to be defined as the distance between x and y is equal to 0 if x is equal to y, and 1 otherwise. So you can check that this is a metric. It's not a very interesting metric, but it is a metric. Okay, so now when we have a metric, we can turn our metric space into a topology. And the way we do this is, it's called the metric topology or the open ball topology. The way we do it is we look at open balls around points, and those are going to form the basis for open sets. So let me clear out some of the stuff from this page now. So we're just going to look at the Euclidean metric right now. Oops. Okay, so open balls. we can define an open ball around a point as it's kind of what you'd expect in the Euclidean metric. However, in other metrics, open balls can look quite strange sometimes. Right, so the open ball around a point is given, it's used with this notation here. So this is the ball around a point X with radius epsilon. That's how you read this. And this is just the set of all points in our space, in our set X, whose distance from X is at most epsilon. So if we look in the Euclidean topology here, let's say this is epsilon right here, and this is X. This would be the ball around X of radius epsilon. Right, it's all points that are it's all points whose distance from X is less than epsilon. And so we can use these balls to define a topology. So the topology is just going to be unions of these open balls. Those are going to be the open sets in the topology. So the classic example is the real line. So in the real line, we looked at it before, right? Here, our open sets here were unions of open intervals. Well, those open intervals are actually open balls in the topology and in the metric. And so we get actually what we looked at on this page, the metric topology. Okay, so now another way we can define a topology on a set is with the subspace topology. So let's say we have, let's say we're in a topological space already. So let's look at just R2 with the Euclidean topology. So we're already in a topological space, and now we want to look at a subset of this space. So be careful here. It doesn't matter if this is open, if the subset is open or closed or whatever. This is just any subset of X. So here X is just all of two-dimensional space, and we're just taking any subset of it. We can define a topology on this subset. Let's call this Y. By the way we're going to do it is we're going to look at open sets in our original space. So here, this is R2. And we're going to just intersect those open sets with Y. And those are going to form the new open sets for Y. So for example, an open set in R2 looks something like this. Really, it's a union of these balls, but still, this is an open set. And we're just going to intersect this with Y. And so this here tells us that this right here has to be an open set in the subspace topology on Y. Okay, and so this is going to be a really powerful tool for coming up with new examples of topological spaces. A lot of the topological spaces we'll be studying are naturally going to be subspaces of certain other spaces, oftentimes Euclidean space. Okay, so now there's a couple operations we can do on subsets. So one is closure. So essentially, the idea behind the closure of a subset is it's the smallest closed set containing it. So if I give you a set A, its closure would be the smallest closed set containing A. Similarly, the interior of A is the largest open set inside of A. And then the boundary of A is given by, so this is a mistake a lot of people make. A lot of people think the boundary is the closure minus the interior, but that's not always the case. The boundary really is the closure of A intersect the closure of A complement. So let's look at an example now. So here we're in Euclidean space, and this is our set A. So the closure here is going to look like all of A, except we're also going to include this, this part here that was left out. So this is the closure of A, which we're going to write as A bar. Okay, but now we can look at the interior of A. On the interior of A, what we're going to do is, right, we want the largest open set contained inside of A. So we need to get rid of sort of these closed boundary lines here. So it's going to look like this. Like that. Yeah. Okay, so this is the interior of A. And now let's go back to where we were. Okay, so now and then finally we can look at the boundary here. So the boundary of A is going to be this whole blue curve sort of around the edge of it. This is the boundary of A. And so we can look at these closures, interiors, and boundaries for any subset of any topological space. Okay, yeah, so that's all for this video. So the next video, we'll be looking at continuous maps between topological spaces.